My name is Mahdi Gulum and today I'll be presenting about frame aggregation and MU-MIMO for the IEEE 802.11ac LAN. First of all, let's have a look at Wi-Fi. It's a wireless connectivity technology that uses 2.4 and 5 GHz band of frequencies that enables a PC, laptop or a handheld device such as a mobile phone or a tablet to connect with the internet at high speed without using a physical wired connection. And for the MU-MIMO, it's a technology that breaks up the available channel bandwidth into separate individual streams that share the connection equally by creating the spatial streams. In other words, MU-MIMO technology increases the capacity and efficiency of the LAN router. MU-MIMO used in the IEEE 802.11ac standard supports up to 8 parallel spatial streams and up to 4 simultaneous users in the downlink. And for the frame aggregation, it's a feature added to the IEEE 802.11ac LAN standard to alleviate the performance of the wireless networks. This is mainly implemented at the MAC layer level of the IEEE 802.11ac standard. Using frame aggregation, the transmitter can aggregate 2 or more data frames in a single transmission, which reduces the overheads such as headers and other control fields, and thereby further increasing the throughput. With the changing needs and increased demands of data rates of the consumers over the time, the development in the IEEE 802.11 standard also resulted in different versions and generations of Wi-Fi. As you can see here, the IEEE 802.11b, A, G, N, AC, AX and BE starting from the year 1999, and the frequency of operation at 2.4 and 5 GHz, and the data rate starting from 1 till more than 9,000 megabytes. The main objectives of this research is to analyze the performance of frame aggregation on the throughput and channel utilization of the IEEE 802.ac wireless networks, and to simulate and analyze the performance of MU-MIMO setting jointly with the frame aggregation in the IEEE 11ac LAN, and to analyze the effect of number of users, frame length, and number of frames aggregated on the performance parameters such as throughput and channel utilization in the IEEE 802.11ac LAN. Let's have a look here. First, we can consider the system model with one access point, AP, and the number of mobile stations as shown in the figure. An access point is connected to the server or a backbone networks and has 8 transmit antennas. Second, for the receivers, they can be any mobile stations, laptop, desktop PC with Wi-Fi network card. We assume that each user station has 2 antennas such that there is 8x2 MIMO channel for each user. Third, the channel between AP and mobile stations support line of sight or non-line of sight RF communications and is technically described as TJAC channels in the IEEE 802.ac standard. We describe the throughput calculation methodology and different parameters considered for the calculation. The following steps are followed to simulate the system in MATLAB. First of all, let's have a look at the figure. We have the transmitter, which first we configure the physical layer basic parameters. Second, we configure the MAC layer parameters and determine the number of frames for frame aggregation. Third, we generate random data bits and determine the frame payload for a number of frames. Fourth, we perform the frame aggregation and generate the aggregated MAC frame. Last, we generate IEEE 802.ac VHT, which stands for very high throughput waveform using physical layer and MAC layer configuration. And for the channel, we define the wireless LAN channel independently for every user and define the receiving antennas and fading module. And then we pass the waveform through the TJAC channel and add Augen noise. And for the receiver, we determine the packet offset and extract the VHT LTF field, then we demodulate the VHT LTF, and this programmable field contains the training bits for channel estimation at the receiver and deaggregate the frames for extracting the data field. Then last we check if the deaggregated frames match with the transmitted frames. If no, then frame error counter increment, else transmit next frame. Do this until sufficient successful packets are transmitted and recovered. Determine the successfully transmitted packets and error packets, then compute the throughput as discussed in the report. Channel utilization is an important parameter to analyze the performance of IEEE 802.11ac LAN networks. Channel utilization is defined as the fraction of average time spent for successful transmission over the channel to the total time taken. We describe the method for computing the channel utilization, and various other parameters are taken. Here we can see mainly three results are presented for throughput analysis: throughput variation with MU-MIMO and frame aggregation with varying number of users, with changing the numbers of frame aggregated and changing the frame length. Let's have a quick demo for each of these three plots. First, we run the program. Okay, in this result we show the effect of increasing the number with increase in the number of users on throughput. Frame aggregation is fixed at 20 and 50 frames. At 50 and 20 and 50 number of frames aggregated. As the number of users join the network, the throughput decreases. This is because as the number of users increase, the total channel bandwidth is divided among the number of users, and average throughput starts to decrease due to small increase in the protocol overhead and increase in the delay serving the different users, and also resulting from acknowledgement phases. It is shown that at the higher channel bandwidth and a greater number of frames aggregated, the average throughput is as high as 1.3 gigabytes. For the second plot, we can see here that as we aggregate a greater number of frames in one packet data unit, the throughput increases. This is mainly because the packet overhead related to the data transmission decreases and overall data transmission increases. Because of this reason, the throughput increases almost linearly up to 50 aggregated frames. This is because of the reason that as we increase the number of frames aggregated beyond 50, the packet length increases and corresponding packet transmission times becomes large enough to create the delays for other users. One user transmission takes large time and the transmission of other users become delayed, resulting in overall saturation of the throughput. Now let's have a quick demo at the last plot of the throughput analysis. Okay, we can see here we plot the average throughput by taking different frame lengths of the users in this figure. Initially, as we increase the frame length in the packet data unit, there is an increase in the throughput because increasing the frame length increases the amount of data transmission, resulting in obvious increase in achievable throughput. But in every case of different number of aggregated frames and different number of users, as we increase the frame length beyond certain limit, the throughput starts decreasing. This is again because of the problem of end-to-end delay. Therefore, we conclude that optimal frame length is required along with the optimal number of aggregated frames to achieve the maximal throughput. Now let's have a look at the channel utilization plots. As you can see here, there are two plots. Let's have a quick demo for the first plot. Okay, we analyze here that as the number of users increase, the effective channel utilization decreases, whereas when we apply the frame aggregation and data packet unit of the users, the channel utilization improves. This is primarily because with the frame aggregation, the amount of data transmission increases, resulting in better utilization of the channel. The packet collisions taking place with the increased number of users, resulting in the reduction of effective channel utilization. And last, let's have a quick look at the last plot of the channel utilization. So here, the channel utilization with number of frames aggregated for different channel bandwidth and number of users. We observe from this figure that with the increase in number of aggregated frames, the channel utilization increases marginally. And for conclusion, we conclude that optimal number of aggregated frames along with the optimal frame length is required to achieve the maximal throughput. That there is always an optimum length of frames where the throughput is maximum. That the optimum length can be different for different numbers of users and bandwidth. As the number of aggregated frames increase, the amount of data transmission increases, and hence the throughput. We also conclude that the frame aggregation has marginal effect on channel utilization, but it still increases the average throughput to a good extent. And for the future scope, it would be interesting to analyze and observe the effect of variation of a frame size across the users while taking different traffic modules with the arrival of packets defined by Poisson Pareto distribution, but that would increase the system complexity. And one can study the effect of distance on the throughput when different users connected to the same AP but are at different distances from the access point. Some users are near to the AP and some users are at some distance. And changing the effect of dynamically changing the MU-MIMO spatial streams requirements per user on the system parameters can be of interest. Here is the main references. I hope you enjoyed my presentation today, and thank you very much.